Okay, so we're still on the random processes. Uh, we've just finished some statistical tools, but this is another tool which is an extension of the PDF procedure that helps us now measure the dependency between two random process. So actually, pag meron kang experimental record na accurate naman siya, at least dalawa lang okay na siya, no? So if you have two records of a certain sort that will that will give you some graph, random graph like this, uh, buhay ka na sa paggawa ng statistical process mo in a probabilistic sense, okay? So this correlation or autocorrelation is simply the measure of dependency between the two processes involved or the two records involved. No? So if I make an experiment, say I shake the table, and this is my my graph of the vibration, in as far as my x2 variable may be a response, it's like this, and then the other response is like this. Then I can now make use of a correlation process to predict the behavior of my experiment at a certain arbitrary value of time t. Okay, so the correlation is done this way in a manner wherein it is calculated by simply multiplying two coordinates. So if I have two coordinates here, or two ordinates, let's say this is my x2 and this is my x1, I simply multiply this, and you expect this to be a large value if these are large individually very large numbers, no? So x1 times x2 becomes a large value if they are large, and they are small values if they are small. Okay, so in this multiplication, what we do is we compute the average of this product over the time domain, which is from 0 to t. Okay, so we compute the average over or with respect to this time domain here. So if I have a lot of points on x here, okay, x there, okay, so I just take the average of this. I multiply x1, x2, x2, x3, x3, x4, and so on, or x1 of 1, x2 of 1, x1 of 2, x2 of 2, and so on. And then I take the average. I'm doing actually what you call a correlation. So that's the correlation process. Okay, and this correlation process is best described by, again, a formula using the limit function or the limit as your function. So as time t approaches, of course, an infinite, okay, if this is an infinitely uh, sample, an infinite sample of a record, then I can make use of the limit ranging from t approaching infinity. Then again, the averaging value is denoted by the 1 over t uh, factor here, okay, and the summation or the average of such is represented by the integration from the range or the domain c 0 to t. Okay, so where are your values, no? So the values are now, these are two experiments or two records. So the one is x of t and the other is x of t plus a certain tau there. So what does this mean? So this can be better represented by an x1 of t multiplied by an x2 of t, but the fact that we are trying to relate the two, what we're going to do later is to make use of what you call a delay or an advance uh, time tau. Okay, so this tau here simply delays or simply advances your graph in such a way that your x1t and x2t will be randomly picked or randomly processed, no? So para hindi siya magpareho. Of course, if they are exactly the same, so much better kasi hindi siya magkakaroon ng stationary anong tawag doon? Stationary graph, just like what we have defined on our first definition of the random process. Okay, and this formula here, which is a representation of a correlation, is actually used and best described by what you call an autocorrelation. So what we are going to do is to correlate it and to autocorrelate it later by using this expression on tau. Okay, so tau is the keyword, no, to deal with the correlation process. So if the two random processes are similar, then again you will just be having a yung average mo will be a straight line. Okay, it will not represent a good prediction on whatever value you are trying to achieve. Okay, so in case they are similar and you put a delay or you can call it a delay on the basis of one experiment, or an advance a lag or a lead time. So lagging and leading is just the opposite of one another depending upon your point of reference, no? You are leading behind if you are referring to the other person, but he is lagging behind if you are referring to yourself. Okay, so which actually makes you or guarantees you of a much more uh, a good representation of your correlation, and this is what you call an auto correlation. Okay, so take note of the two. They are just actually the same, but they are different in the sense that you want to capture a more non-trivial function to achieve your objective of predicting, no, of predicting some tendencies. So parang ano lang yan you are looking into the pattern, and by using statistics, you are justifying that this is the most likely to happen in terms of probability. Okay, so kesa yung you just graph it in terms of a deterministic function and that let everything depends on the function itself. So ito talagang based siya sa mga data na na-record mo, no? Okay, for dissimilar records with mean is equal to 0, which means that some are positive and some are negative, their product will of course approach 0, no? So if you take a value wherein the 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 data are what not similar, and their average or the mean is almost 0, let's say positive 10 and negative 9.8, pag in-average mo yun is almost 0, no? So if you take the product of those which approaches 0, will give you some what? Anong mangyayari pag yung product niya is approaching 0? So wala kang makukuha dun sa correlation mo, okay? But for almost identical records, and then applying the concept of lagging and delaying, no, the occurrence of such event or data to happen, mas maganda, okay? Which represents now this part here, which is x of 1t or x of t. You can remove the subscript 1 kasi wala naman yung x2 na, no? Will be almost identical to x t plus tau. Then the correlation between them is known as the autocorrelation, and this is the best description of what the correlation process is all about. Okay, so if you are asking me what is correlation and autocorrelation, they're just the same, but the objective of autocorrelation is much specific than correlation itself. But in general, autocorrelation is a correlation. Okay, in fact, when we are using the word correlation in statistics, we don't even bother to say it in terms of autocorrelation. Okay? And in figure 22.10, this can actually be seen. So when tau is equal to 0, the autocorrelation will simply reduce to this mean square value. That is this term. So remember again the formula for the mean, the average value. Di ba ganito lang siya? Okay? So we only take note of the mean squared value, So ito lang siya, di ba? Kapag yung tao mo is 0, yung delay mo is 0, which means to say that you have exactly the same record. Okay, so here, if there is a record that is exactly the same, such as this one, so dito na papasok yung autocorrelation. Okay, and what is autocorrelation? So autocorrelation is simply letting one record or one sample or one data history to be lagging behind the other, or you can say it in the other way around, no? One leading in front of the other. Okay, so this is leading in x of t. Let's put it here, x1, x2. If this is your x1 and x2, so as to simplify the function, so we can say that x1 is actually leading from x2, and x2 is lagging behind x1. So it's the same. So what is important is you know how to measure the lag or the lead time tau. Okay, so because later we have to visualize how it works in order for us to use the process of correlation or autocorrelation. Okay, so before we proceed, let's talk about wideband and narrowband processes. So a wideband is simply a random process that is very highly randomized process, and a narrowband is simply a random process that contains a dominant frequency. So this is an example of a highly random process or a wideband process ito. Okay? So when you say highly random, talagang wala kang nakikitang pattern. Can you see a pattern here? You don't see a pattern. It's wide band. No, the spectrum of values of X is really very, very high. Many, too high. Very random talaga. And earthquake, sometimes the earthquake records looks like this. And sometimes meron din part na it becomes a narrow band. Kaya very again this process of using the correlation and autocorrelation is very appropriate in earthquake engineering. Okay? And on the right side of this is the autocorrelation function derived from the uh, record, no, the random function or the data in the random process. So ito yung autocorrelation function niya, or simply you can call it a correlation function also. It doesn't mean anything. Pinag-iba lang kasi in-explain mabuti kung paano na derive yung ganito. So if I will plot now the equation R's of tau in this regard to merong tau dito, no? Okay, I will get a similar graph such as this if my data is highly randomized. Okay, so for a narrow band in which there is a dominant frequency of having a value, ayan, no? Hindi na, parang may pattern na siya, no? Meron ka na nakikita na pattern, frequency, ayan, di ba? So this is now a narrow band process. And the autocorrelation is like this. And if you will just look into the comparison, this is actually symmetrical in terms of the horizontal axis. And the value is not as high compared to the values at the center than at the tail ends. Pero dito is gradually decreasing at a sort of an exponential function. Parang decay siya, no? It's actually a very gradual and smooth decrease in the value of your autocorrelation function. Ito abrupt yung decrease. So if you will look at the sudden decrease here, it's from a very high and then very low there, and then okay, something like that. While here is a gradual decrease. Okay? Okay, so how do we now go about the process? No? So better if we solve an example here. So this illustrative example is a good illustration on how to apply autocorrelation process or principle. Of course, we have to start with the very simple periodic functions in order to understand how it works. Okay, so for the function depicted in the figure below, so it's actually a periodic function. We are asked to determine the mean square, and the autocorrelation function, and we are asked to plot it. Okay, so this is now my function, my record function, or the random function based on the recorded data. It's actually periodic in nature. So nakikita ko itong mga ganitong klaseng functions, class, random behavior sa marami sa mga electrical engineering tsaka electronics. That's why I'm just curious kung magko-consult kayo sa mga magagaling sa ganito, yung mga electrical engineers, okay? Because they are actually studying all about signals, no? Yung mga yung signals ng electricity tsaka electronics, no? Pulse wave modulation, okay? So, sa acoustics, marami ring magagaling. So, pwede kayong magtanong on this and then relate it to structural vibrations. Parang ganun lang yun eh, no? Siyempre, hindi mo i-apply sa electronics. So, I'm just telling you that you can consult other experts, not just in the field of civil engineering, but also in other engineering disciplines when it comes to these random vibration concepts. Okay, so the problem here has a peak value, a maximum value of XO, and the graph is actually a very periodic, no, very typical graph in which your period is simply taken in terms of one pattern, no? Isang pattern lang ito, no? So, and this is your period T, okay? Ang pattern lang niya, it's up, 0, down, and then 0, and then start again up. So, itong pattern na to, pag inulit ko, yun pa rin, up, 0, down, 0. Okay? Pag inulit ko pa rin, ganun rin. So, this is just basically the same all throughout. And it is observed that since the function is periodic, averages calculated over long time approach, if you take the average up to infinity, nagsasayang ka lang ng oras, no? So you might as well do it on a single period. Okay? So ito yung isa na lang ang pag-aralan mo. So for the period, and that is for the period 0 to t. So the function is described analytically by these equations here. Okay, so i-graph mo lang what is this equation. X is equal to a fixed value XO from 0 to T2, or mean to say from 0, this is not X class, this is T. Okay, 0, okay. So this is the t-axis. And xt is equal to 0 from t equals t2 up to t. Okay, so that is your representation in terms of the equation of the graph. So for the mean value, all we need to do is to use the formula. Okay, 1 over t, the integral 0 to t over 2. Okay, xo dt equals simply ano. So you just simply make use of the integral of dt is t, substitute t over 2 there, and then 0. So that is parang mali. So let's check this. Integral from 0 to t2. Okay. So this is not complete. Okay, so we are only referring to the first part of the graph. So the second part is 0. 0 naman siya. So still, if you add the integral from t2 to t of xo dt, okay, so this is, so what will happen there? So xo is 0 there. So this will still be 0. Okay, so the value now is 1 over t. What's the integral of, or x? What's the integral of dt? So this is t. Okay, so this is 0 to t over 2. Okay, so this is xo times t over 2 all over t. So cancel. So the answer must be xo over 2. Okay, let's check on our reference the answer later. Okay, so wala yung... Okay, so let's check this because this is only xo. Okay, for the mean square value, for the mean square value, we have 1 over t xo squared dt. Okay, so this is now, again, if you will substitute this because this is 0, so nothing will happen. So this is equivalent to xo squared all over 2 quantity, same, no? So this will simply be t 0 to t2. Okay, so this is now t2 xo squared. So t2, this is 0, so this must be, and this has a t here. Bakit may 2 dito? Wala, ano? So this is x over t. Okay, x squared over t. So this becomes xo squared over 2. So this is correct because this will cancel, that will cancel. Okay, so you just double check the answers there. This is x squared over 2, this is xo over 2 there. Okay, let's check it later. Para hindi na tayo ma-stuck. Okay, so that's the mean square, that's the mean value. Now for the, I'm interested with the autocorrelation. Okay, let's look here. On the autocorrelation function, it is necessary to distinguish the time shift tau. Okay, so ito ngayon ang key, no? So the key on the autocorrelation is this one. Okay, so this is your formula for our tau. Okay, xt plus tau dt. So you have to find first what is your tau. Okay, let's look into how these two equations were met. Okay, so the question here is, how did you get this? Okay, so let's look at figure 24.15. Okay, so remember what I told you a while ago about the one lagging behind and the other leading. Okay, leading ahead of the other or lagging behind the other. Okay, so let's assume that your first record is the solid line. Okay, so this is the first record, solid line. Okay, and the second record is the dotted line. So the dotted line is this one. Okay, so for your autocorrelation, what you do, since these are similar records, okay, you have to make sure that one is lagging behind the other. Let's say the second record is lagging behind the other at a distance of tau here. Okay, so this is now your lag time tau. Okay, so this green line is lagging behind the purple line. Okay, so this is tau, and we know that the distance between this whole uh, graph here, this whole line here has actually a distance of t over 2. Okay, such that the remaining distance that is autocorrelated, okay, so the word now is autocorrelated, yung parang they're the common area para sa Venn diagram. The area common to both is the autocorrelation, which represents the distance t over 2 minus tau. Okay? So this is now the basis for your domain 0 to t over 2 minus tau. Okay, it starts, the autocorrelation domain starts from 0, this is 0, up to t over 2 minus tau, this now. Okay, 0 up to t over 2 minus tau. And then since they are similar records, you just square it. Okay? So that's how easy you can think of the process. If you can do it in this very simple, you can also do it in a difficult, kumbaga, yung record, no? Magtsatsaga ka lang, okay, in defining what will be your autocorrelation domain. Yung domain mo kasi doon makikita mo siya. Okay? And that is only one part or one phase of the whole period. Because this is periodic, remember that this is 0 to a certain part, dapat meron pang kadugtong yan. Hindi pa dyan nagtatapos. Okay. So, ano yung kadugtong? The other possibility is the one, the second graph is leading ahead of the first graph. And this is now the second figure, 24.15. Okay, so in 24.15, this is your first record, and this is your second record, which is already leading. Actually, it's pwede ring lagging behind dun yan, no? Pero if you will look at it, you have to look at it on two aspects. Sabi ko nga, when the dog wags his tail, pwede mo sabihin yung tail ang nagwawag doon sa dog. Tama? So, or vice versa. You can interpret it as the ground moving while the building is stationary, or the building is moving while the ground is stationary. So it depends on how you look at it, and you have to look at it in two aspects because you are autocorrelating the two. Okay, so for this autocorrelation now, the thing here is you will be starting here. You started at the green, so this is now the solid line, the dotted line here. You have to start also with the green, which is the dotted line there. And the starting point here is from t minus tau. Okay, so this is now your first point. So if you look now on the limit, okay, your lower limit is t minus tau. Okay? So it starts with t minus tau up to this point. Of course, you are looking you are looking again at the autocorrelation, which is an intersection, the common area intersected. And if you will just look into the project this on top, this is actually t over 2. Okay, so you are now ranging from the autocorrelation domain starting from t minus tau to t over 2. So this is the one that is important because your function is very simple. Ito yung magdadala. Now, if the function is difficult, still your key is the solution to your start and the end points of the domain. Of course, this is not a continuous again. It's not a continuous function. It is a discrete function. So you have to take care of discretization or discretizing point by point. Kaya kailangan magkaroon ka ng dalawang uh, uh, representation. Okay? And doing this integration procedure both will simply yield a result. Okay? And it is easy to integrate. No? This is easy to integrate. Ito, ginawa ko naman pala dito. Akala ko hindi. Okay, so if you integrate that, your integration will simply have your x o squared all over t, just like what we did with the mean and the mean squared. And then this is just the upper limit, okay, minus the lower limit. So this is the upper domain minus the lower domain for the first, okay. And for the second, your upper domain is this one and your lower domain is this one here, okay. So it's minus t plus tau, okay, and then your t over 2 is the upper domain, okay. And if you take a look at this, these are just the same equation, only the signs are different. No, this is a positive negative, this is a negative positive, which means to say that they are just what, the mirror of each other. No? If you have a line that is what, almost the same in terms of their parameters, but the sign is different. Okay, so it's just a line actually. It's mx plus b, no? Here, this is your mx, this is your intercept, this is your mx, this is your intercept, something like that. Okay, so if you will look at this, there must be symmetry on the graph, and if you will graph that, of course, your resulting graph will be simply this one here. Actually, what represents your graph is only this, but since this is periodic on the basis of the period t here, it will just repeat, going to positive infinity to negative infinity. So this is what you call now the autocorrelation function RT for the function which is periodic in nature as described in example 22.2 of this problem. Okay, so thank you class for listening. I hope you gained something about this random variable. If we will have some time next week, I will be discussing to you maybe an introduction on the